Hello, my name is Rocio Vidalis, and I will be sharing you my results and conclusion from Lab 1 in my introductory physics class at Georgia Tech. In this report, I will share with you the purpose of the lab, the results from my observational and computational models, their differences, and then conclude their results. To solidify and extend my knowledge, I will also answer some conceptual questions. The purpose of this lab is to follow through an experiment where an object, in my case a small soccer ball, is moving at a constant speed. The ball is the system, and the surroundings are the concrete it is on it and the force of my push. This observational model will be shown on the Tracker app. Then I am to mimic the constant velocity from the force through a computational model on GlowScript. After I take the graphs of both, I will be able to see the differences between both models. Before I begin, there are concepts we must understand. Newton's first law of motion states that an object at rest will remain at rest unless a net force acts on it, and the same goes for an object in motion remaining in motion unless a net force acts upon it. Newton's second law of motion states that force equals mass times acceleration. We need these laws for the velocity and position update formulas on the screen. Another note to keep in mind is that I consider there to be no friction or resistance on the ball, so our net force is equal to 0. If the net force is 0, I can state that the ball is in constant motion. For this reason, I uploaded a video onto the Tracker app that included the push on my ball, so that it is only a video of the ball in constant motion. Tracker recorded its position over 1 second. Here's the graph of my ball's position at each time. Keep in mind that the slope of my graph is negative because I set the left to be negative x. Also, there are forces in the real life that slow down the ball, so our graph is not a perfectly straight line. As you can see, its starting position was at negative 0.0006 meters and ended at negative 0.473 meters. These are the key elements needed for our computational model up next. Mass can be put to the side for this experiment and therefore cancels out the following formula I will show you. I found my initial velocity to be negative 0.39 meters per second through the average velocity formula. Delta t was also found to be 33 out of 1,000 from the frames per second of my camera. I input these into the code. The while loop runs for the same amount of time as my ball video, and I input the formulas from the introduction. Here is the computational model's graphs for position versus time and velocity versus time. This graph comparing the two models shows the perfect computational model slope versus the observational slope with real-life forces infringing upon it. For further understanding, I must ask myself, what if I were to orient the axis? Well, the x-axis is negative on my experimental models because I set the left to be negative x. But if I were to flip it to make a positive slope, then that would mean that I have set the right to be negative x. There is also the other question of, is it possible for me to say how many pushes and pulls are on the object? No. It's not possible for me at the moment. This is due to us not accounting the multiple forces present, such as friction and air resistance on the ball. Those are the same forces also that made the observational model be different to the perfect computational model's slope. In conclusion, I have found that it is still possible for an object to remain in motion even if there is no force present. There being no force present means that the object is in constant motion and velocity. In the real world, as you can see, there will always be forces like friction and gravity acting upon moving objects, making it hard for an object to remain in motion. And that concludes my first lab in introductory physics. Thank you.